Oh, there. So in today's lecture, we're going to carry on from last time, looking at a few more things that we can do with our Minkowski metric for space-time. So before we get to that, let's just do a quick recap on the whole space-time and metric thing. So the way we model space-time, or should I say flat space-time, is with just R4. Okay, so we have a four-dimensional space, so we can represent each point in the space by a coordinate with four entries. The way we do that in special relativity is we say that the first entry is time. However, we need to multiply it by c just so that all the entries have space units. But a lot of the times we just let c be equal to 1. Okay, so instead of writing c's and c squares everywhere, we just say we work in units where c has the value 1, and then we don't need to write it. If we do want to go back to normal SI units, then we can just look at the units and see where should we put in the values of c or c squared. We'll get to that later on. So let's just leave c there for now. So the first entry by convention is time. We multiply by c just to get some space unit there. Then we have our x, y, and z as usual. Now, as soon as we write down this coordinate, we are implying that we're using some sort of coordinate system. So, for example, these unprimed coordinates, let's say this is my choice of coordinate system. Okay. So here I've used the so-called Cartesian coordinates, but I can choose my origin, I can choose my scaling, anything like that. Okay, so that can be my choice. You could choose something else. You could have c t prime, x prime, y prime, z prime. That can be your choice. Okay, so maybe you also like Cartesian, but maybe you've got a shifted origin, for example. Maybe you want your origin to be where you're standing, or anywhere. You can pick whatever you like. You could also choose something else. You don't have to stick to Cartesian. You could have something like CT, R theta phi, for example. Okay, maybe you want to go to spherical coordinates and you want to do special relativity in that coordinate system. Maybe your friend's label or your friend's choice. So you see the actual choice of coordinates doesn't matter, okay, as long as you stick to it. However, just for simplicity, we're going to be sticking to the Cartesian choice. Okay, but of course, we can go to polar coordinates or spherical coordinates. As long as you know how to go from one coordinate system to another, then everything is fine. Okay, and we will look at that later on. We'll look at a very special set of transformations to go from one Cartesian type coordinate system to another, the so-called Lorentz transformations. Okay, so that's something like between the unprimed and the primed in these first two cases. Okay, and of course you could go from Cartesian to spherical, but then that would be another type of coordinate transformation. Okay, but all of that is just labeling our points in space-time, okay, which we model with R4. Now, just as is, when I say R4, usually you would think Euclidean space, where we measure distances using Pythag, right? You know, your normal distance formula. However, we can't assume that because here we're going to be using a different formula to calculate distances. We're going to use the so-called Minkowski metric. We're going to use that to find distances. And if you did the homework from last lecture, you would have seen the differences between using the different metrics. So if you use the Minkowski metric to calculate the distance of a world line, you get one answer. If you use the Pythag Euclidean metric, you get a different answer. So it really does affect what you can measure. Okay, so it's important to know what we're using. Okay, so on this R4, we have ourselves a metric given by ds squared is equal to c dt squared minus dx squared minus dy squared minus dz squared. Sorry, that's a z. Okay, and just for convention, here we're using the plus, minus, minus, minus metric. Of course, you can use the other one. You're free to do that, but you need to stick to your choice. You can't go you can't go changing between signatures in a calculation. Okay, then you're going to get something wrong there. And of course, this is the metric in Cartesian coordinates because we've got dt, dx, dy, dz. If we were working in spherical coordinates, this metric would then look different, okay, because you're in a different coordinate system. Okay, maybe I will put that as a homework problem. So homework. Write ds squared in spherical coordinates. Okay, that's a good homework question. Just to show you how we can go back and forth between two coordinate systems. Okay, so I'll leave that for homework there. But for assessments and stuff, we're going to stick to the simple Cartesian coordinates. Okay, now remember that this metric is coordinates independent. So writing it down, of course, we need a coordinate system to see what the components are. However, this ds squared, as I wrote here on the left-hand side, is invariant with respect to the coordinate systems. So if you write it down in Cartesian, or you write it in terms of the primed Cartesian, or you write it in terms of spherical, it's all different representations of exactly the same thing. Okay, so we're going to use that idea to find a very short derivation of the so-called time dilation and length contraction phenomena. Okay, all explained using the metric and the use of two different coordinate systems. So that's where these phenomena come from. So if I'm viewing something, I will say that I see X. If you view something, you say you see Y. Now, why are they different? It's because we have two different viewpoints on this thing. Okay, but objectively, it should be the same thing. Okay, so let's take a look at the first phenomena of time dilation. So as always, we begin with the metric. That is the central thing that we work with. So ds squared in, let's say, my coordinate system, the unprimed, we can write it as c squared dt squared minus dx squared minus dy squared minus dz squared. Okay, so this is what I write down for my representation of the metric. Now, you also have your metric, but you're going to write it down differently. So let's say in my system, I am moving. Okay, so this dx, dy, dz, that's going to be changing. In your system, let's say you're not moving. Okay, so, well, technically you're not moving through space, but you are moving through time. So for you, you're going to have c squared dt bar squared. Okay, so I'm just going to put a bar instead of a prime, just because of the exponents are going to get messy. So we have the bar is for the prime coordinate system, or your one. So this first part here, this is moving. This one here, not moving. However, they are equal because this ds squared doesn't care about your choice of system or coordinate system. So we've got this relationship between the two metrics, the one that I'm using, the one that you're using. We're going to see what we can get from this. So first, let's divide through by c squared. Okay, so we're going to have dt squared minus dx squared plus dy squared plus dz squared, all over c squared, is equal to dt bar squared. Okay, good. Let's divide through by dt squared now. So we're going to have 1 minus, let's take the c squared out there, dx squared over dt squared plus dy squared over dt squared plus dz squared over dt squared. Okay, that's equal to dt bar squared over dt squared. Okay, now this dx over dt squared, that's the same thing as just writing x dot squared. So we're going to have 1 minus 1 over c squared, x dot squared, plus y dot squared, plus z dot squared, equals, and then we can write this as dt bar by dt squared. Now, x dot squared plus y dot squared plus z dot squared, that's just your velocity squared. Okay, if you add up all of your components of velocity, you get your total velocity. So that's 1 minus, let's say it's v. Okay, sorry, I said your velocity, this was my frame. So I'm the one moving, so my speed is v. Okay, and then we have our dt bar over dt squared. Now we can take the square root. So we can have the square root of 1 minus v squared over c squared is equal to dt bar over dt. Okay, good. Now I just want to solve for dt. So we have dt is equal to dt bar over the square root of 1 minus v squared over c squared. Okay, now this term here, this 1 over square root 1 minus v squared over c squared, this comes up so much in our calculations. What's typically done is we say that this is our gamma term. So we say gamma of v is equal to 1 over square root 1 minus v squared over c squared. Okay, it's just to simplify things. So instead of writing the square root all of the time, we just write gamma. Okay, so we see that on the left-hand side, we've got dt, which is my dt. Remember, I'm the one moving here. So this represents a change in time. More specifically, we can imagine that this is the time interval between clock ticks. Okay, so it's like, how do we measure time? It goes tick, tock, tick, tock. Each of those is a dt interval. So this is the interval between clock ticks. Okay. Okay, so that's my dt. So if I had a clock with me, this is the interval between the ticking. Okay, on the other hand, the dt bar, this one over here, is the interval, or you can think of it as like the period between your clock ticks, or the interval between your clock ticks, anything like that. So the interval between clock ticks for you. Yeah. And then for this one, I should say for me. Okay, because we've got two different views of what's going on. We've got me with my coordinate system and how I measure changes in time. You've got your coordinate system and how you measure changes in time. However, they are related by the metric, because if I put all of this, if I substitute that into the metric, I'm going to get my version of the metric. you're going to get your version of the metric. However, the metrics must be the same. Okay, so if I measure a length through space-time and I get an answer, it better be the same as your answer. Okay, so for example, the length of string, it doesn't matter what you measure the string with. If I use my ruler or your ruler, let's say your ruler had was in inches, mine was in centimeters, for example. It doesn't matter what the scaling is, doesn't matter what ruler you use, the string has the same length. Okay, so that's what we've got here. It's very analogous. So in my moving system, think of it as me using a ruler with centimeters. That's my choice. For your not moving system, so it's your system, you're using a ruler using inches. However, we have to measure the same thing. Okay, like the length of the string must be the same. Okay, so what we've got here, this relationship between dt and dt bar is like the relationship between the centimeters and the inches. It's how we measure that. Okay, and just a quick note on this relationship. If we draw this gamma factor as a graph, so let's say here's v, just here's speed of light c. It starts off at 1, and then it goes up and up and up, asymptotically here at c. Goes off to infinity. Okay. In other words, this gamma is not valid for anything greater than the speed of light. So we've got the speed of light limit over here. Speed limit at v equals c. Okay, so we can't go past that speed limit. You may have heard this as the speed of light is your maximum speed for the universe. We're going to be looking at that in more detail later on. But for now, in this gamma factor, we just need to know that gamma goes off to infinity as we get closer to this speed of light here. Okay, the exact reason for this we will look at later on. Okay, so that's this gamma. And we see that's the relationship between these two. So we've got dt, that's for me, is gamma of v, depends on your velocity, or should I say my velocity, because I'm the one moving, dt bar. Okay, so what does this mean? So for you looking at me, for example, you're standing there and you're looking at my clock, for example. I'm moving, but you can still see the hands tick. What do you see as that tick rate? And conversely, if I'm the one moving and I look at your clock, what do I see as your tick rate? Okay, we're going to be seeing different things because of this relative motion. So here, moving observers ticking, sorry, the comma, apostrophe, moving observers ticking is longer than the stationary one. Okay, because of this gamma factor. Okay, this gamma factor between the two observers here. And notice if v, this velocity, is very, very small, okay, compared to the speed of light, so let's say we're somewhere over here, then this gamma factor is almost 1, which means that the two ticking rates are the same, which is what we experience every day. So if you're walking past me, I'm not going to see that your clock is substantially slower than my clock. Okay, you know, they're going to be pretty much equal. Okay, very, very small correction because of the relative speed. However, as the speed gets closer and closer to the speed of light, we see that there's much more of a difference between these two rates. Okay, and that's because of this relative motion between the observers. Okay, so this is our conclusion here. Okay, we call this time dilation. Okay, dilation like stretching, because the time interval between the ticks is getting longer for this moving person. So we call this time dilation. Okay, so that is the stretching out of the time periods. Okay, we can do a similar derivation here for the other phenomena of length contraction. Now, I've done this derivation for the time dilation, so I'm going to leave this for homework. So homework. Use a similar derivation to find the formula for time dilation. Sorry, length contraction. Sorry, we've done time dilation. Okay, so it's the same sort of thing. We have ds squared for me in the moving frame, ds squared for you in the not moving frame. But now we're not measuring the ticks of a clock. We're now measuring the length of an object. Okay, but it's the same sort of thing. We equate the metrics and then find the relationship between the two lengths measured. So what we will see is L is equal to L naught square root 1 minus V squared over C squared. Okay, you should be getting that. So this L, this is the measured length in the moving frame. Okay, so if you're moving, that's L. And then L naught, we call this like the rest length. Okay, that's the length. If you were standing next to this object, not moving relative to it, and you were to measure the length, you would get this. So this is the so-called rest length. Yeah. Later on, we will look at the so-called rest mass, but I don't want to do that. I don't want to call it rest mass. We should be moving away from that. Your mass is just your mass, okay? If you are moving, then you have this extra energy that just adds to your energy. So you have some higher effective mass, for example. But I don't like that concept of rest mass. So your mass if you're still, your mass if you're moving, that should be the same. There is actually something else that you're measuring where your mass is increasing in quotation marks. Okay, so for rest length, that's fine, okay, because you're at rest with this thing. However, when we get onto mass and so on, I'm going to do it a bit different to what the past lecturer did. Okay, so I just keep that in mind. Okay, so we get this formula here for length contraction. So we see as the velocity increases, this length is going to get smaller. Okay, hence length contraction. Okay, so I'm going to leave that for homework. Just follow the same steps as we did for time dilation, except we're not solving for dt and dt bar. Here we are looking at some length interval like dx. So dx and dx bar, for example. Okay, some interval of length, not an interval of time. Okay, so that's going to be for homework. Okay, so we're going to leave the metric for now, looking at things we can do with the metric. We're going to talk more about that later on when we get onto velocities and momentum and energy and so on. We'll get back to this. But for now, we're going to be looking at a single metric, but going from one coordinate system to another. Okay, so not like the special case of moving and not moving, something a bit more general. Okay, so let's take a look at that. So length contraction, and time dilation are special cases where we choose two different coordinate systems. For example, the one was not moving, it didn't have any change in X, Y, or Z, while the other was moving. Okay, but that's just a special case. So length contraction and time dilation are special cases where we choose different coordinate systems. And we saw interesting things from that. What we're going to do now is look at a case that's a bit more general. So we're going to look at coordinate transformations from unprimed, so let's say CT X, Y, Z to CT prime, X prime, Y prime, Z prime. Okay, so it's a bit more general than what we had before. Last time here with this coordinate transformations, we saw that dx bar, dy bar, dz bar, those were all 0 in this special case. But now we're not going to be looking at that. Okay, something a bit more general here. Okay, so what is the relationship between these two? Well, like I said, if you're measuring the length of a string, doesn't matter what coordinate system you're using, the length of the string is just the length of the string. So in fact, we have ds squared is equal to c dt squared minus dx squared minus dy squared minus dz squared. Okay, that's just in the unprimed system. We can do exactly the same thing in the prime system. We can have c dt prime squared minus, c squared minus dx prime squared minus dy prime squared minus dz prime squared. Okay, and these are equal. Okay, so whether you use the one system or the other system, we get the same metric. Now, we're going to be looking at these transformations between the two. Okay, the so-called Lorentz transformations. Okay, just a coordinate transformation. Okay, now before we get on to that, since we are treating time and space as almost equals, of course, the metric still picks out time as something special there. However, the fact that we're using t, x, y, and z separately like that means they are pretty separate still. So what we're going to do is define new variables that make them more equal than what we have here. So we define x naught to be equal to c times t. Okay, so it's a length quantity. So speed times time, that's a length. We call that x naught. Then x1 is just going to be x as we had it before. x2 is going to be y, and x3 is going to be z. So you see we're kind of unifying these into one variable x. Okay. So altogether, the label of a space-time point is going to be, x naught, x1, x2, x3. Okay, this is our space-time coordinates. Okay. So you see how it's a bit more unified than what we had before. So we're going to be using this from now on. And remember the conversion from time to some distance quantity, we just multiply by c. So if we want to go backwards, we know where the C's should go. Okay, and another thing that we need to define, if we look back at our definition of gamma, we had this relationship between the velocity and the speed of light. It was V over C. Okay, so that ratio of your velocity versus the speed of light, that ratio we also give a name we call beta. It's going to be V over C. Okay, so that's just two definitions that we make. Just a redefining the labels for a space-time coordinate and this new term beta, which is V over C. And just note V over C, this is unitless. Sorry. Unitless. Okay, so we've got a speed at the top, speed at the bottom. The units cancel out and we just get a number beta. Okay, so you can measure it in meters per second, kilometers per hour. You still get beta. Okay, so let's look at the relationship between our unprimed and primed coordinate system, keeping in mind these definitions we've made here. Okay, so I'm just going to write out the Lorentz transformations, or Lorentz boosts, as they're sometimes called. So we're going to have x naught prime is equal to gamma x naught minus beta x1. Now, the first thing you should notice is when we're going from primed to unprimed or unprimed to primed, notice how we are mixing space and time together to get the new coordinate. So the new time coordinate, okay, in quotation marks, the new time coordinates, the x naught, is a combination of the old time coordinates and the old x coordinates. Okay, they're actually being mixed there. So if you're using one system, what you call time, okay, so let's say you're in the prime system, what you call time, for me, is actually a combination of space and time. Okay, so there's this mixing of things. So like I said in the past lecture, these coordinates, the time, x, y, and z, they really depend on the coordinate system that you use. So what is time for you might actually be space for another person. And there's always this coordinate transformation between the two. So this idea of universal time where everyone agrees on what time is, what the value of time is, that's gone now. Okay, because of this mixing behavior between the coordinates. The time for the prime coordinates is a combination of space and time for the unprimed coordinates. Okay, there's this mixing going on here, and we need to be aware of that. Okay, then x1 prime is going to be, sorry, there's a gamma missing there. Gamma x1 minus gamma beta x naught. You see, again, we've got this mixing here. So in the prime coordinates, what you call x, that's your x direction, for me is actually a mixture of time and space. It's a combination of things. Okay, I'll draw a diagram now illustrating this. Okay, now the way we've written it now is these two coordinate systems are based on two systems moving relative to each other, but only in the x direction. Okay, so time and x get mixed, the others remain the same. So x2 prime is x2, and x3 prime is just x3. So the way we write this is I've got my x and t. Okay, so I'm just going to go back to x and t just for this illustration. So that's your one, and then my one is x prime t prime, and I am moving relative to u with speed v. And we know that v divided by c, that gives us our beta term. Okay, so we've got this relative motion only in the x direction. Okay, if we were moving in the y direction, then this would be different. Okay, so this is a so-called boost in the x direction. If we were boosting in the z direction, then it would be time and the z component that would be mixing. Okay, if we were going in some other direction, then there would be a different kind of coordinate transformation. Okay, so this is a boost in the x direction. Okay. Now, since y and z remain the same, because we're only moving in x, we can just leave those out. Okay, so these parts here, they remain the same. We don't have to worry too much about that. However, these first two lines, they are important. Okay, so another thing we can do is notice that this is just a linear combination. We have x0 and x1 on the right-hand side in linear combination. Now, as soon as you have linear combinations of things, we can go back to our linear algebra and realize that we can write that as a matrix. Okay, so we've got two linear equations. We can write it as a matrix. So we're going to have, we're going to have x0 prime, x1 prime is equal to the matrix that is doing this linear transformation. Just compare coefficients here. We can see it needs to be gamma minus beta gamma, minus beta gamma, and gamma, and x0, x1. So this gives us the coordinate transformation matrix to go from unprimed to primed. Now, this is a linear transformation from unprimed to primed. It's a very special case of the transformation. For example, we could do a coordinate transformation that is very nonlinear if we wanted to. Okay, but if it's very nonlinear, we can't write it like this matrix transformation. Okay, so please keep that in mind. If it's a linear transformation between two coordinate systems, we can write it as a matrix product. Okay, because matrices and linearity, they go hand in hand. However, if it's a non-linear transformation, we can't use matrices anymore. So this is a very special case of a coordinate transformation. Of a coordinate transformation. Okay, so later on, when we look at other quantities like velocity and energy and so on, those will be in vector form. Okay, much like how we wrote this position in vector form. However, for those, we will see that when we are transforming coordinates, the non-linear coordinate transformations actually relate to linear transformations in those components. Okay, not necessarily linear transformations in terms of coordinates, but it is a linear transformation for velocity and momentum and vector quantities like that. Okay, so please keep that in mind. Okay, so this is, again, a very special case of a linear coordinate transformation. You could do non-linear, that's perfectly fine as well. Okay, but then you can't write it as a matrix, of course. So another way of writing this is x prime. This is the so-called position vector, okay, in Minkowski space. But I don't like calling it that because position shouldn't be a vector. Position is a point. A point is labeled with a coordinate, not with a vector. Okay, so we have x prime is equal to, we usually call this capital lambda. So like an L for Lorentz transformation, and then x, like that. So this is the relationship between x prime and x. Sorry, and x. I've got another homework question. So this is the relationship between the unprimed coordinate system and the primed coordinate system. So going from unprimed to primed, you multiply by this lambda. If you want to go back, you need lambda inverse. So find lambda inverse such that we can go back. So we can have lambda inverse times x prime is x. Okay, we want to go back. Okay, so find lambda inverse and its relation to lambda. Okay, there's a very nice relationship between the two in terms of the velocities or in terms of the betas. So take a look at lambda inverse and notice how the betas change and what does that relate to in terms of, you know, real physical space, or physically, what does that relate to? How does this lambda inverse relate to, let's call it physical observation? In other words, if you're standing here and you are in the unprimed, so let's say this is unprimed, and I am running away, let's call that primed, with speed v. Okay, so we can use this lambda to go from unprimed to primed, or lambda inverse to go from primed to unprimed. But what is this relationship with v? Okay, and how does that relate to this physical picture over here? Okay, so I don't want to give too much away. I'd rather you figure that out yourself. But what's the relationship between these two people and their views or their physical observation of what's going on? Okay, so going from lambda to lambda inverse, how does that relate to this physical view of what's happening, for example, with the two people? Okay. Okay, so that's one of the homework questions for this. And then the last homework question for today. Show that this capital lambda, the Lorentz transformation, show that this Lorentz transformation leaves ds squared unchanged. Okay. In other words, ds squared in the primed system, ds squared in the unprimed system, they should be the same. So far I've just been saying that they should be the same, and I gave you a physical argument. For example, the length of the string should be just the length of the string. It doesn't matter what kind of ruler you use. However, we never showed that explicitly. So now in this homework question, for this specific example of a transformation, show that this ds squared is unchanged. Okay, so your ds squared and my ds squared, how are they affected if you are using primed coordinates and I'm using unprimed coordinates? Okay, so have a look at this and you should see that ds squared remains the same. Another way of writing that is it's invariant under coordinate transformation. Okay, so it's independent of how you actually measure things. And we will see later on at other invariants, other quantities that are invariant, for example, your mass. If you're in one coordinate system and I'm in another coordinate system, your mass is your mass. That shouldn't change. Your velocity does change if you're going from one coordinate system to another. We're going to measure different velocities, of course. However, we will look at the so-called force velocity, which is your velocity through space-time, and that is invariant. Okay, so in one coordinate system and in another, your force velocity remains the same. Similarly, your force momentum, that is also the same. It should be invariant. Okay, and we will look at some other invariants as well. And another one is the action, which is what we're going to be looking at in the next lecture. Okay, so the action is like the proper time. It is invariant under coordinate transformation. Okay, so as always, if you have any questions, please let me know on the WhatsApp group. I'll be happy to answer you there, or you can just send me an email. I can answer you there as well. Okay, but in the next lecture, we will be looking at the action, how we define the action, why we define it that way, and how we can use it to find the force velocity and the force momentum such that they are invariant. Okay, because remember, we don't want to be worrying about coordinate systems. The things we define should be independent of that. Okay, I'll see you next time. But please, if you do have any questions, let me know and try out the homework problems. I will upload the solutions at the end of the week. Okay, bye.